A recent observation by scientists has revealed a shocking fact. When the sun sets and night falls, Mercury, the seemingly silent planet, actually slowly releases certain substances into space. A quiet yet magnificent emission is quietly unfolding in the darkness. Imagine being on the surface of Mercury, not in the scorching inferno where the daytime temperature soars above 400 degrees Celsius, hot enough to melt metal. Instead, you're witnessing a completely different side of Mercury, a polar world that you've never seen before. At this moment, you're in the long night of Mercury, a night that lasts longer than a month on Earth. There is no dawn, no afterglow. Time passes slowly, as if the entire planet is trapped in a stagnant slumber. The sun disappeared below the horizon weeks ago, and the remaining heat is gradually dissipating. The next sunrise is still weeks away, a result of Mercury's extreme rotation cycle, where one rotation takes almost as long as 2 revolutions. The sky above is crystal clear, and the deep blackness spreads out like velvet. Since Mercury has almost no atmosphere, the stars don't twitch or shimmer. Instead, they are as sharp and clear as laser points. The light from each star shines directly into your eyes without distortion, as if the universe is revealing its most primitive appearance to you. You're wearing space boots with extreme heat insulation. Beneath your feet is a surface that was extremely hot during the day but is now cold. The rugged rocks are slowly releasing the heat they stored during the day into the surrounding vacuum. Without air to carry away the heat, the process relies solely on thermal radiation. This is a completely desolate scene. There is no wind, and sound waves can't travel. There is only the silent solitude of the vacuum. The cratered landscape, shaped by countless meteorite impacts, makes it seem as if the whole world has been frozen in a moment from the ancient past. But on this night, you're not just a traveler trying to survive. You're carrying more than just a heat-insulating suit and an oxygen supply. You have a set of extremely sensitive and precisely calibrated observation instruments. You are an observer, ready to uncover the secrets that this planet hides in the dark. You skillfully activate a high-resolution spectral detector and turn it to a very narrow wavelength range between 589.0 and 589.6 nanometers of the sodium emission line. Then you aim it steadily at the so-called anti-solar point, the position directly opposite where the sun is below the horizon, an area often overlooked but full of potential surprises. Just as everything is set and the telescope is precisely focused, you suddenly discover that unprecedented light trace. It's a phenomenon that can only be seen in a specific wavelength band. What appears before your eyes is a silent wonder, something that almost doesn't belong to this world. It's as thin as smoke and as ethereal as the lingering breath of a ghost. Its existence is so fragile that it could blend into the background starlight if you're not careful. It's a slender and transparent light band, like the fingertips of a ghost, slowly stretching out from the night side of Mercury and pointing straight into the depths of the universe. It has no boundaries and makes no sound, as if the planet is writing a letter in the dark, telling the universe about its existence. It's an extremely delicate optical structure that can't be captured with the naked eye and only appears within the narrow wavelength range of the D-line. It's as gentle as a whisper of light, stretching nearly to 0.5 million kilometers, like a long robe of light draped over Mercury as it wanders in the darkness of the solar system. Mercury, the planet that has long been considered almost dead, with a cooled interior and no dynamic atmospheric activities, is showing astonishing dynamic behavior in the deepest darkness. It's performing a graceful yet spectacular show where our eyes can't reach. Yes, this rocky planet is emitting a tail, a real tail, similar to that of a comet. However, it's not made of a mixture of ice fragments and dust. Instead, it's composed of a stream of atoms that arouse our curiosity. These atoms spill out from the surface of Mercury and slowly disperse in the direction of the solar wind in the dark. This comet-like tail is not composed of gases formed by the sublimation of water ice or tiny dust particles, which are the components of a traditional comet's tail. Instead, it's made up of a more definite, unique, and intriguing element. This element can exist in a high-temperature environment and has the property of emitting light. The answer is sodium, a metallic element commonly found in table salt on Earth. But in the extreme environment of Mercury, it appears in a completely different form. Sodium becomes the source of the faint light and the main material of this ghostly tail. These sodium atoms are ejected into space at a speed of several kilometers per second. Today, we will delve deep into one of the phenomena accidentally captured by space telescopes, Mercury's huge but invisible sodium tail. A multi-layered phenomenon that combines planetary physics, the interaction between sunlight and particles, and spectral observation technology. It is also one of the most low-key yet amazing natural mechanisms in the solar system. We will start from the initial discovery, learn how this sodium tail emerged in the observational data, and understand through what scientific reasoning it was linked to Mercury. We will also analyze the physical processes behind the formation of this tail, including how the solar wind strips atoms and how meteorite impacts trigger the release. We will try to understand the continuous dynamic interaction of energy between Mercury and the Sun. When it comes to planets in the solar system with dramatic or unique features, we often think of Saturn's rings, Jupiter's great red spot, or Olympus Mons on Mars. But rarely do we immediately think of Mercury, this underestimated small planet that seems to lack astonishing characteristics. Mercury, the smallest planet in the solar system and the one closest to the Sun, has long been regarded as a small rocky sphere governed by gravitational and radiative pressures. Its surface is covered with meteorite craters and thermal cracks. One side is as hot as a furnace, while the other is as cold as ice, resembling a bare rocky remnant in the universe, seemingly unremarkable. However, a turning point that changed our perception of this planet quietly occurred in 2001. That year, the astronomical community suddenly noticed an unusual signal coming from a celestial body that we thought we already understood, triggering a series of exciting follow-up studies. Back in the mid-1980s, astronomers had already detected the presence of trace amounts of sodium atoms in Mercury's thin exosphere. This discovery made us realize that even in such an extreme environment, Mercury still has some degree of atmospheric dynamics. So, scientists began to use a sodium filter, an instrument that can isolate specific wavelengths and specifically detect sodium emission lines, to conduct continuous observations of Mercury. This was exactly what the team from the McDonald Observatory in Texas did in 2001. They aimed these specialized filters at Mercury, trying to understand the structure and changes at the edge of its atmosphere. But they unexpectedly observed that beyond the planet itself, in the area far away from Mercury, there was a faint but distinct sodium haze extending far beyond the disk of Mercury, like a leaked fog of light. At first, the researchers were confused by the observation results in front of them and even suspected that this should not be in line with the existing theories. According to the models at that time, Mercury simply could not generate a material flow at such a long distance. They repeatedly checked the calibration status of the telescope, confirmed that there was no redshift drift in the filter, and reanalyzed the original data, wondering whether there were errors in the spots generated by the charge-coupled device or deviations in the algorithm during image stacking. However, after ruling out all possible systematic errors, the truth became clearer and clearer. This was not an illusion of the machine or noise in the data, but a huge structure that truly exists in space, a phenomenon that we had completely overlooked before finally revealed itself in the glow of light. Mercury, the small planet closest to the Sun with a seemingly unassuming appearance, is actually dragging behind it a sodium tail structure that stretches nearly to 0.5 million kilometers along its trajectory. This is more than 6 times the distance from the Earth to the Moon. It is an extremely thin but astonishingly long river of atoms, quietly spreading in space. To truly feel the shock of this proportion, we can make the following conversion. Mercury has a diameter of only about 4,880 kilometers, but this tail is 700 times its diameter, like a small stone dragging an almost invisible ribbon in space, showing us a new scale of planetary phenomena. This discovery is almost a slight humiliation for the astronomical community. We knew so little about this planet that has been observed since ancient times. Such a huge structure had been hidden right under our noses for so long and was only revealed in the 21st century. Mercury is neither a mysterious celestial body in the outer solar system nor a circumplanetary object hiding at the edge of the asteroid belt. It is one of the planets in our solar system that is closest to the Sun and not too far from the Earth. It is visible to the naked eye and has been recorded since ancient times, dating back to the times of ancient Babylon and Greece. From ground-based telescopes to orbital probes, Our exploration history of Mercury has exceeded half a century. In the 1970s, Mariner 10 provided the first close-up images of this planet. And in the 2000s, the Messenger went a step further, orbiting Mercury and mapping its magnetic field and geological structure in detail. However, even so, this sodium tail was like an invisible cloak, evading our attention. It was not until the 21st century that, through more sophisticated filters and improved spectral technologies, we realized that Mercury has been showing its presence silently in a nearly poetic way beyond our sight. And this sodium tail is its most mysterious and inspiring evidence. The significance of this discovery lies not only in the technological breakthrough, but also in its impact on the astronomical classification system. Tails have almost been the exclusive feature of comets in the past, but Mercury's sodium tail breaks this framework, indicating that the interaction between planets and stars is much richer and more complex than we originally understood. Suddenly, the image of Mercury has been completely reversed. From a dry place full of impact marks, it has transformed into a dynamic planet with a tail that extends millions of kilometers, a surprising celestial body with a spectacular gaseous structure that can be on a par with the most active comets in the solar system. So, here comes the question. What is the fundamental difference between this tail extending from behind Mercury, which looks like a comet's structure, and the tails of real comets in terms of both origin and composition? Why would a rocky planet like Mercury, which has no glacial activities, generate a long tail composed of metal atoms? It is neither like a comet nor like other planets or satellites. So, where does its tail come from and why is it made of sodium? The answer can be attributed to the convergence of three key elements: Mercury's extremely close orbital position to the Sun in the solar system, the unique chemical composition of its surface geology, and the strong particle flow and radiative pressure released by the Sun itself. These three elements have intertwined to create a rare and fascinating astronomical phenomenon. Typical comets can be imagined as ancient snowballs composed of ice and dust, orbiting the solar system in an elliptical path, sometimes moving away from the Sun and sometimes getting closer. Every time they return to the inner solar system, it's like a cruising evaporation. The main components of a comet's nucleus are various volatile ice substances, including water, carbon dioxide, and ammonia. When they gradually approach the Sun, these ices start to directly transform from solid to gas, which is the so-called sublimation. During this process, mixed dust is also swept up, forming the familiar coma and tail, a glowing trace composed of ions and debris that escapes along the direction of the solar wind. In sharp contrast, Mercury is a rocky planet, similar to the Earth or Mars, but drier and more desolate. In its crust structure, almost no volatile ice components can be detected. Based on radar and infrared observations, researchers speculate that traces of water ice deposits might be preserved in Mercury's polar regions, especially at the bottoms of craters that never see sunlight. These ice deposits persist solely due to the combined effects of topographical shielding and extreme cold. Otherwise, they would have evaporated completely under the Sun's rays. This means that Mercury's striking tail doesn't originate from the sublimation of ice, but rather from the direct release of metallic elements, particularly sodium, from its rocky surface. Sodium is an element that can be easily excited to emit light and readily escapes from the surface, exhibiting high activity in high-energy environments. The questions remain: why sodium and not other elements? And what triggers the release and ejection of these sodium atoms? To solve this mystery, we must revisit Mercury's close relationship with the Sun. This proximity not only shapes its landscape, but also profoundly influences its interaction with the cosmic environment. When Mercury reaches its perihelion, it comes as close as about 47 million kilometers to the Sun, nearly one-third closer than Earth's orbit. As a result, it endures solar radiation about 10 times stronger than that on Earth. Such extreme sunlight creates highly favorable conditions for the excitation and release of surface atoms. In addition to light and heat, Mercury also lies in the path of intense solar winds. These are continuous streams of high-speed charged particles emitted by the Sun, acting like invisible plasma hurricanes that constantly batter this unprotected, exposed planet. Picture a supersonic stream of electrons and protons hurtling towards Mercury at speeds approaching 400 kilometers per second, about 1.6 million kilometers per hour. a relentless torrent of particles crashing into its bare rocky surface. When ions from the solar wind impact Mercury's surface, they convert their kinetic energy into impact energy, forcefully dislodging atoms bound to the surface. This process, known as sputtering in physics, is a classic form of interaction between high-energy particles and solids. To better visualize this, imagine your refrigerator door covered with magnetic stickers, each representing an atom adhered to Mercury's surface. These magnets stay firmly in place until disturbed by an external force. Now, envision throwing a bouncy ball hard at the refrigerator door. The impact is analogous to the high-energy strike of a solar wind particle. When the ball hits, shockwaves spread across the surface, causing vibrations. Some magnets, especially those with weaker adhesion, become loose. If the impact energy exceeds the magnet's holding force, they pop off exactly how atoms sputter off Mercury's surface. This is the essence of the sputtering cascade. One particle initiates a chain reaction, transferring energy layer by layer until surface atoms are released into space. When the high-speed ion stream of the solar wind slams into Mercury's surface, the energy it releases targets the atoms with the weakest binding forces. In Mercury's crust, sodium atoms are among the easiest to dislodge, like the magnet with the least suction getting hit by the bouncy ball. Sodium indeed has one of the lowest binding energies among metals in Mercury's surface layer, making it highly vulnerable to release by solar wind particles. This directly explains why it forms the main component of the tail. It's easily excited and carried away. Data collected over time by NASA's Messenger spacecraft, which orbited Mercury, reveal that during periods of heightened solar wind activity, especially during coronal mass ejections, more high-energy particles bombard Mercury's surface, causing the concentration of sodium atoms in its exosphere to surge by an average of 50%. This demonstrates a strong physical coupling between the solar wind and the planet's surface. These observations strongly support the core hypothesis: the stronger the solar wind, the more frequent and intense the impacts on Mercury's surface, prompting more atoms to break free from the solid surface, spill into its thin atmosphere, and ultimately form and sustain that elusive yet magnificent sodium tail, making the tail a dynamic indicator of solar wind strength. However, the solar wind is only half the story. To fully understand the birth and evolution of this tail, we must also consider another continuous yet destructive cosmic force: impacts from space dust. Besides enduring constant solar wind bombardment, Mercury stands like an unshielded outpost, continuously pummeled by streams of cosmic projectiles from across the solar system. These tiny space rocks would burn up completely in Earth's atmosphere. But on airless Mercury, each one becomes a high-energy impact. In a world devoid of an atmosphere, without any means to slow down or burn up, even a dust particle less than 1 millimeter in diameter strikes the surface at tens of kilometers per second, generating instant heat and shockwaves capable of vaporizing surface atoms and altering the geological structure. When these dust particles hit Mercury's surface at high speeds, the intense, instantaneous heat they generate vaporizes the rock material at the impact site. This not only releases existing atmospheric molecules, but also liberates sodium atoms trapped within the surface layer, injecting them into the planet's exosphere and further elongating the tail of light. In a sense, Mercury is undergoing a silent cosmic erosion, a slow but relentless process of disintegration that has persisted for billions of years. This planet, unable to escape the onslaught of solar and cosmic forces, gradually sheds its surface atoms into space, steadily losing mass. Some observational analyses indicate that the intensity of Mercury's sodium tail significantly increases during specific periods, which closely coincide with the times when its orbit crosses certain interplanetary dust streams, especially the debris trails left by short-period comets like Encke's comet. This suggests a direct link between dust density and the rate of sodium release. When Mercury passes through these dust streams, micrometeoroid impacts surge, enhancing the impact vaporization efficiency. This causes more sodium atoms to escape from the surface into the exosphere, where they're then pushed by sunlight to form a brighter, more observable tail, resulting in the tail's periodic brightening. Notably, while Mercury's sodium tail may visually resemble a comet's iron tail, the physical mechanisms driving and shaping them differ dramatically. For comets, their tails are mostly the result of iron flows directly blown by the solar wind. In contrast, The extension of Mercury's tail isn't driven by particle thrust but by a more subtle yet persistent force: radiation pressure. In fact, it's the light emitted by the Sun that, through an extremely delicate but cumulative mechanism, with photon radiation pressure as the primary driving force, shapes Mercury's sodium tail. This causes the stream of metallic atoms to extend in an almost linear fashion away from the Sun. This force may be too weak to detect. The momentum of a single photon is minuscule. However, when billions of photons continuously strike the same group of atoms, the cumulative effect becomes significant enough to push the entire tail outward in the airless expanse of space. Although photons have no mass and can't collide with atoms like physical particles, the momentum they carry still generates a noticeable tiny thrust when absorbed by atoms. This is known as light pressure, the same physical principle underlying the operation of solar sail spacecraft and the formation of Mercury's sodium tail. When sodium atoms floating in Mercury's thin exosphere are irradiated by solar radiation, they absorb photons of corresponding wavelengths, gaining momentum away from the Sun. This causes them to undergo extremely subtle but continuously cumulative acceleration at the atomic scale. Although after absorbing a photon, a sodium atom will spontaneously emit a photon in a random direction within an extremely short time frame, theoretically creating some momentum cancellation in the opposite direction. These random directions tend to neutralize each other, resulting in an average recoil force that's negligible. The process doesn't end there. The sodium atom quickly returns to its ground state and is ready to absorb the next photon from the Sun. This cycle repeats. Within just a few seconds, an atom might be pushed hundreds of times. This is the fundamental driving force that allows the ghostly tail to persist and expand. As sodium atoms continuously absorb photons from the Sun, they accumulate minute but consistently directed momentum. It's like an invisible, extremely gentle yet relentless solar wind, day after day, pushing these atoms away from the Sun, forming a stable and elongated tail. You can envision each sodium atom as a tiny solar sailboat suspended in the heights of Mercury's exosphere, constantly unfurling its invisible sails and gliding slowly using the momentum provided by solar radiation. Thousands upon thousands of these atoms converge to form a river of orange, yellow, optically translucent streams. Although the force of light pressure is weak, over time, it can overcome the feeble gravitational pull of Mercury's surface. This enables the released atoms to continuously move away from the planet, eventually extending into a structure spanning millions of kilometers, detectable from Earth using specialized equipment. Since the driving force of solar radiation pressure is unidirectional, always pointing from the Sun into outer space, Mercury's sodium tail remains steadily oriented opposite the Sun, towards the so-called anti-solar point. Thus, the tail's direction serves as a natural indicator of radiation pressure, reflecting the Sun's ongoing influence in space. However, as we mentioned earlier, despite its incredibly vast spatial scale, the tail is extremely tenuous, too faint for the human eye to see directly. So, how did scientists discover and confirm the existence of this almost transparent tail? When sodium atoms absorb energy from external sources, whether from solar photons or particle impacts, their outer valence electrons gain enough energy to jump to higher energy levels, entering an excited state. This is a common physical basis for all luminous atoms. Once the excited electron loses energy and returns to its original ground state, it emits a photon with a very precise wavelength, around 589 nanometers. This is the famous D line in the sodium atom spectrum, the optical fingerprint for identifying sodium. This 589 nanometer yellow-orange glow may be familiar to you. It's the color emitted by traditional high-pressure sodium vapor lamps. That warm yet slightly shadowy golden hue is a common sight in urban nightscapes, a practical manifestation of sodium's spectral characteristics in our daily lives. In Mercury's sodium tail, this luminous process occurs constantly. Tens of thousands of sodium atoms absorb, get excited, and emit light simultaneously, creating an invisible optical symphony. However, due to the tail's extreme thinness and the faintness of the emitted light, it's nearly invisible to the human eye and conventional telescopes. To capture this almost transparent tail, astronomers developed a highly specialized tool, the D-line filter. This filter allows only light within the narrow 589 nanometer wavelength band to pass through while blocking all other wavelengths. This makes the faint glow of sodium atoms appear like ghostly flames in the darkness. Using these highly sensitive spectral filters, background starlight, solar scattering, and other noisy wavelengths are effectively eliminated, leaving a clear view. On this pure black canvas, the thin orange, yellow filaments emitted by sodium atoms finally become visible, like a delicate optical silhouette. This technology is like tuning into a single track in the chaotic spectrum of the universe, allowing us to hear the melody that was previously drowned out by the noise, the beautiful glow of Mercury's sodium tail. During Mercury's approximately 88 Earth-day orbital period, the length and brightness of the tail don't remain constant but fluctuate significantly depending on the planet's position. Mercury's orbit is a distinctly elongated ellipse rather than a circle, causing its distance from the Sun to vary significantly during its revolution. This is the starting point of the tail's periodic changes. When Mercury reaches its closest point to the Sun, the perihelion, the solar radiation and solar wind pressure it experiences peak. This makes the detachment, excitation, and sputtering of surface atoms more frequent, especially increasing the rate and quantity of sodium atom emissions significantly. Based on these conditions, one might intuitively assume that Mercury's sodium tail should be brightest and most observable at the perihelion, as it's when energy input is most intense and conditions are most extreme. However, actual observations reveal a more complex scenario. Surprisingly, the peak observable intensity of Mercury's sodium tail doesn't occur at the perihelion but around 16 days after Mercury passes it. This time lag indicates a physical delay and cumulative effect between the tail's formation and its maximum manifestation. Let's delve deeper. This seemingly contradictory phenomenon hides a highly intricate astrophysical mechanism. Mercury's elliptical orbit means its speed isn't constant. It varies drastically depending on its distance from the Sun, ranging from about 39 kilometers per second at aphelion to nearly 59 kilometers per second at perihelion. This variation in speed is one of the key clues to the observed delay. Through long-term systematic observations and data comparisons, researchers have found that around the 16th day after perihelion, Mercury's radial velocity, its speed of moving away from the Sun, reaches its maximum. This maximum radial velocity plays a crucial role in tail observations. In other words, during this period, Mercury is moving away from the Sun at its fastest speed. This not only stretches the tail physically, making it longer and more diffuse, but also creates observational advantages, making signals that were previously obscured by the Sun become brighter and discernible. The key question is, why does the faster Mercury moves away from the Sun, the brighter its observed sodium tail becomes? The answer lies in a classic optical phenomenon explained by two words: the Doppler effect, also known as Doppler shift, a wavelength shifting phenomenon we can experience daily in the siren of an ambulance. In astronomical observations, it's a crucial tool for decoding spectra. When we analyze the white light emitted by the Sun with a spectrometer, the otherwise continuous spectrum shows narrow black lines. These are Fraunhofer lines. They form when sunlight passes through the Sun's atmosphere, especially the photosphere and chromosphere. Some photons of specific wavelengths are selectively absorbed by elements there, leaving these dark marks, like cosmic chemical fingerprints. Among these absorption lines is the sodium D line, precisely at the key wavelength of 589 nanometers. Since the Sun's own atmosphere is rich in sodium ions, when sunlight radiates outward through its outer layers, the wavelength band around 589 nanometers is significantly weakened. This means that the sodium, emitting light originally from the Sun, is partially consumed before leaving the Sun. However, when Mercury moves away from the Sun at a high radial velocity, a significant optical phenomenon occurs. The entire solar spectrum shifts towards the red end due to the Doppler effect, i.e., the wavelengths are stretched. This means that the sodium D line, which was originally absorbed by the Sun, now shifts to a different position, freeing up the 589 nanometer frequency band. This shift is like stretching a rubber band. The distance between wave peaks increases, and the 589 nanometer wavelength, originally corresponding to yellow light, is pushed into a redder band. This is the classic redshift phenomenon, also a vital tool in observing cosmic expansion and exoplanets. As the solar spectrum shifts towards the red, the Fraunhofer absorption lines originally overlapping at 589 nanometers are also displaced, restoring the photon supply in that wavelength region. At this point, the sodium atoms in Mercury's tail can finally absorb the pure, unabsorbed sodium emitting light, get excited, and radiate, making the tail particularly bright during this period and creating a prime observation window. After this complex interplay of physical processes and observational conditions, what results do we actually get? Ultimately, Mercury's once hidden ghostly tail becomes significantly brighter under optimal conditions, allowing us to observe this slender stream of light from Earth using precise instruments, revealing the secrets of planetary activity through the night sky. Does this mean that astronomers can easily spot this tail by looking in the right direction 16 days after Mercury passes the perihelion? Far from it. In fact, such observations require overcoming numerous astronomical and optical challenges. The timing is precious, and the conditions are extremely stringent. Perfect observation conditions are rare. To observe this elusive sodium tail, besides getting the timing right, 3 key observational geometric conditions must be met simultaneously, and each can be a make or break factor. First, during observation, Mercury must have a sufficient angular separation from the Sun, i.e., a large enough visual distance in the sky. If it's too close to the Sun, even a bright tail will be overwhelmed by the Sun's glare and become unobservable. Second, Mercury's position must be to the side of the line of sight between the Earth and the Sun, not behind it. Once it enters the so-called inferior or superior conjunction from our perspective, it will be completely obscured by the Sun, making observation impossible. Third, and most challenging, telescopes on Earth must be able to aim precisely at the anti-solar direction of Mercury, where the tail points. If the geometric alignment is off, even if the tail exists, it will be out of our line of sight, making it difficult to distinguish or completely invisible. Such an astronomical configuration with all 3 conditions met is extremely rare, often occurring only once every few years. Therefore, every successful observation is a perfect combination of opportunity and technology. In fact, when scientists at the McDonald Observatory first observed Mercury's tail in 2001, it was almost entirely a serendipitous discovery. They accidentally stumbled upon the perfect observational window, creating one of the most iconic happy accidents in modern astronomical history. This was a true example of how the right time and place and intricate arrangement by the universe itself allowed us to glimpse a secret that should have remained hidden at the Sun's edge. Some of the most stunning images of the sodium tail were captured by ground-based observatories equipped with coronagraphs. These instruments are ingeniously designed to block out the intense sunlight, essentially acting as sunglasses for the Sun. Even when Mercury is close to the Sun, coronagraphs can isolate the faint glow of the tail from the blinding background. Behind each clear image of the tail lies the result of months or even years of observation planning and orbital calculations. These images are not just pictures, they represent triumphs in our understanding of cosmic mechanisms. These rare visuals showcase the ribbon-like dynamic changes of Mercury's sodium tail. It stretches and contracts, its brightness flickering in response to variations in sunlight and wind pressure. Choreographed by the principles of precise orbital mechanics and quantum excitation, it performs a cosmic ballet, a dance between celestial bodies and atoms. However, this isn't just a story about Mercury. It's a window, a crucial cross-section that allows us to observe how an entire planetary system interacts with its parent star. The sodium tail is like an optical litmus test, revealing processes that were once almost impossible to measure. It offers us a glimpse into how stars erode their planets, how particles interact with solids, and how gravity and radiation compete. Moreover, it enables us to generalize these mechanisms from our solar system to the entire galaxy. Firstly, it provides a new perspective on the long-term evolution of planets, especially those without protective atmospheres, which are constantly exposed to high-energy radiation and particle winds. We can study how these celestial bodies are slowly eroded, transformed, and perhaps even disintegrated. Although the rate of sodium loss is extremely low, negligible on the scale of a human lifetime over the billions of years of the solar system's existence. These slow losses gradually deplete the most easily dislodged elements on Mercury's surface, such as sodium and potassium. This, in turn, subtly alters its chemical composition and spectral signature. By observing this atomic depletion process, we can extrapolate to other ancient planets in the solar system under similar conditions, speculating about which key elements they may have lost over billions of years. This has profound implications for understanding planetary aging and chemical evolution. Secondly, and perhaps most excitingly, this seemingly esoteric phenomenon on Mercury has opened a new door to understanding exoplanets' worlds orbiting distant stars, providing an unprecedented observational method and theoretical framework. Over the past 20 years, astronomers have discovered that many extrasolar star systems contain so-called hot Jupiters. These gas giants, similar in mass to Jupiter, orbit extremely close to their parent stars, moving at high speeds in extremely hot and radiation-intense environments. If a small rocky planet like Mercury can generate such a vast tail under intense sunlight, then these massive hot Jupiters, under extreme conditions, may experience even more dramatic mass loss, forming longer and denser gas tails that could potentially be detected from afar, a kind of planetary scale fluid ejection phenomenon. Today, many spectral observation techniques and filtering methods derived from Mercury research are being adapted and expanded to detect whether these exoplanets also exhibit elemental tails or signs of gas escape. These tools have become stellar microscopes for exploring distant planetary systems. When we observe faint but distinct absorption features in the spectra of distant stars, such as abnormal spectral lines of sodium, hydrogen, or calcium, it may indicate that planetary material is being stripped away and dispersed into interstellar space. This provides indirect evidence for inferring the atmosphere structure, internal composition, and even magnetic field strength of these exoplanets. Mercury isn't alone. Even our Moon has been found to have a faint sodium tail, formed through similar mechanisms driven by solar wind sputtering and light pressure. This suggests that in the solar system, all celestial bodies lacking atmospheric shielding may have their own atomic tails, observable when the conditions are right. Thus, Mercury's sodium tail is not just a local phenomenon. It's a natural experiment across scales, allowing us to deduce and validate the physical processes of star-planet interactions from a real-world example in an extreme environment, whether in our own solar system or at the far end of the galaxy. By carefully studying this seemingly minor phenomenon, we are gradually piecing together a more complete picture of cosmic evolution. Stars are not only the source of light and heat for planets. They are also powerful forces that continuously erode and reshape their planetary systems, altering the chemical, physical, and orbital fates of planets over vast timescales. To further unlock the mysteries of Mercury and its tail, the BepiColombo mission, a collaboration between the European Space Agency and the Japan Aerospace Exploration Agency, has already completed 6 precise flybys of Mercury. This is both a scientific and navigational challenge. In December 2025, BepiColombo is set to enter Mercury's orbit officially, commencing a primary mission phase that will last at least 1 year. At that time, with unprecedented instrumental resolution and observational perspectives, it will conduct in-depth studies of Mercury's crust, core structure, and exosphere dynamics, including closely tracking the formation, changes, and correlations with solar activity of the sodium tail. This mission is expected to return high-resolution data that can not only map the spatial distribution, density fluctuations, and periodicity of the sodium tail, but may also uncover underlying interaction mechanisms that are currently not understood, adding more mysteries and clues to this already astonishing phenomenon. Mercury's almost invisible tail serves as a reminder that even though this planet has been within human sight since ancient times and has been studied by telescopes and spacecraft for centuries, we have only scratched the surface of its secrets. This is the essence of science. There is always another unknown waiting to be discovered. It makes us wonder, do our familiar neighbors, Mars, Venus, and even the Moon, hide similar phenomena yet to be revealed? Are we merely touching the thinnest veil of cosmic truth? Perhaps the greatest wonder of the universe lies in its ability to never stop astonishing us. Whether we are observing a star, a dark spectral line, or a barely perceptible sodium tail, as long as we continue to explore, the answers will eventually emerge. Mercury's sodium tail is a trace of light, the footprint of atoms being pulled apart between gravity and radiation. Invisible and intangible, yet millions of kilometers away, it tells the story of how a planet slowly sheds its outer layers under the sun's gaze. This isn't just a story about a small planet. It's about one of the oldest relationships in the universe, that between a planet and its star, between matter and energy, between time and loss. Behind Mercury's slender, elusive tail, we see not just the glimmer of sodium atoms, but how planets age, how stars dominate, and how, bit by bit, we reconstruct the history of the entire solar system and, by extension, the universe from these almost silent signals. Every time we look up at the sky, we aren't just observing, we are listening to the echoes of matter. The future may not lie among the stars themselves, but in the shadows of the light they leave behind.